We all know how to multiply a number by a fraction, but what does it actually mean to multiply a number by a fraction? It means that you repeat the number less than one time. Okay, well, what exactly does that mean? And in what kinds of situations would people have invented such a strange notion? Let's find out here on Inductica. Unit 1.21, multiplication of a whole number by a fraction. Motivation 1. We'll start our journey once again with Bar, who's a local businessman in the city of Babel, who uses methods of fractions to gain an edge in his business transactions. Today, the young trader Bays has approached Bar with a business proposition. Bays proposes that Bar should give him some gold so that he can take that gold and buy some goods in Babel. Bays would then travel to Seshatet, sell those goods for a profit, use that money to buy goods in Seshatet, then return to Babel and sell all of those goods for a profit. Bar and all the other investors would then share equally in whatever Bays made. Now, of course, Bays would also take a fee. Now, this didn't seem quite right to Bar, so Bar asks Bays if he could see the list of investors and all of the money that each of them contributed. And that list looks like the following. First, Ram, a character from one of our earlier stories, has contributed 100 gold coins to the adventure. Then we have Hadar, and he has contributed 150 gold coins to the adventure. Rouge, 20, and Bays has himself contributed 90. Now, Bar immediately recognizes that it isn't fair for the investors to split the gross, that is the total income, of this adventure equally, since the investors didn't contribute equal amounts. Now, Bar himself wants to contribute 240 gold to this venture. Now, after adding all of this up, Bar finds that the total investment would end up being 600 gold coins. Now, once again, Bar knows that each of the investors should only be paid in a way that reflects the amount that they actually invested in the venture to begin with. The way Bar thinks about it is he thinks, well, however much we end up getting paid from this, let's think of that as one whole piece of bread. Bar has been working with fractions for a while, so that's the way he tends to think of things. And he says, let's say all of the gross is one big old piece of bread. If that were the case, then I would be entitled to 240 slices out of 600 slices of that piece of bread. And in like form, Ram, for example, would be entitled to 100 slices out of 600 slices of that piece of bread, etc., etc. So this leads Bar to the following question. Question 1. How can fractional parts of a total be allocated to different investors? Investigation 1. Bays tells Bar that after his fee, he expects to take back 1,300 gold from this adventure. That's what he expects to be the income. Now, if this were the case, Bar knows that he's entitled to 240 out of 600 shares of this 1,300 gold. Now, to make this easier, Bar knows that he can simplify this fraction. So first, he divides both the top and bottom by 10. That gives 24 over 60. Then he divides the top and bottom by 12. That gives 2/5. As a result, what Bar knows he has to do is he has to break the total gross, the total income from the trip, into 5 equal shares and then give himself 2 of those shares. So first what he's going to do is he's going to take the 1,300, he's going to divide it by 5. 1,300 divided by 5 using division, which is a prior induction, is 260. Now that's one of the shares and he's entitled to 2 of such shares. So he's going to do 2 times 260, which is 520. So as a result, Ram knows that he's entitled to 520 gold if Bays does in fact come back with 1,300 gold. Just to make sure he understands this method, Bar is going to practice it a little bit to figure out how much Ram would be entitled to if in fact Bays ended up coming back with 1,300 gold. Now remember, Ram invested 100 gold, which means he's entitled to 100 shares out of 600. This is, of course, a fraction that's kind of difficult to work with. So we're going to reduce the fraction. As a result, we're going to break the investment into shares of 1/6, and Rom is going to get one of those shares. So first we're going to divide the investment 6 ways. 1,300 divided by 6. We're going to use perfect long division, which is also a citation to a prior video. And once you do that division, you get 216 and 2/3. Rom is entitled to only one of those shares, so we multiply by the top, and the top is 1, so nothing happens. And so Rom is entitled to 216 and 2/3 shares. So in general, the way this method works is you take the total, and if someone is entitled to a 2/5 share of that total, you first divide the total by the denominator, and then whatever that comes out to, in this case 260, is the quantity of one share. You then take that quantity, times it by the numerator, and the numerator is, of course, the number of those shares that the person is entitled to. Once you make that multiplication, that's the part of the total that that investor is entitled to. Motivation 2. Barr wonders if he can think of this problem as being 2/5 times 1,300. The reason he thinks he can do this is because, first of all, this did involve the fraction 2/5, and he feels like what he's doing here by allotting himself 2 shares, each of 1/5 each, he feels like what he's doing is he's repeating 1,300 2/5 of a time. That's a little weird because it implies that you can multiply something by less than 1, but it seems to make sense to Barr, and so he wants to figure out if this is really a valid way of thinking about it. Now, when he thinks about it, he realizes, yeah, this is a valid way to think about it, because first I'm dividing by 5, cutting the total into 5 equal shares, and then I'm giving myself only 2 of such shares. So this number really is repeating 1,300 2/5 of a time. Now, Barr realizes that this process is very similar to multiplying 2/5 1,300 times. So when you have it in this order, it means 2/5 1,300 times, which is the commutation of 1,300 repeated 2/5 of a time. If we think back to a previous induction, when we multiply a fraction by a whole number like this, we first multiply by 2, then divide by 5. This process of repeating it by a fraction is the same thing, but just done in reverse. We first divide by 5, then multiply by 2. So that leads Barr to the following question. Does the multiplication of a fraction and a whole number commute? So in order to figure this out, Barr is going to think about this example. He's going to think about 1,300 times 2/5, repeating 2/5 1,300 times. So the way he chooses to think about this is first what he does is he says, okay, first let's just think about having 2/5. Each of these fifths is multiplied by 1,300, so that's just 2,600 fifths. Once you have it written like this, you of course reduce the improper fraction to a whole number with a prior induction. Now Barr wants to understand if this is equivalent to doing 2/5 times 1,300. This way of thinking about it is you take 1,300 and repeat it 2/5 of a time. Now, when he thinks about this, whether this is equivalent to this, thinking about 1,300 repeated a partial time, it's really hard to tell if it's the same as this whole process of reasoning. So he thinks of a different way to conceptualize 2/5 times 1,300. Now, instead of thinking of the 1,300 repeated 2/5 of a time, the way Barr thinks about it is he thinks about each of the 1,300 sweet cakes. So imagine each of them right here. And he's going to repeat each of those individual sweet cakes 2/5 of a time. So he imagines having 2/5 of a sweet cake, simply having 1,300 copies of that. That is 1,300 repeated 2/5 of a time, since each of the individual cakes is repeated 2/5 of a time. Now in this case, since each cake has only 2/5 in it, since it's been repeated 2/5 of a time, it's 2/5 times 1,300, which is 2,600 fifths, which is the exact same as what we had in the previous situation. As a result, Barr is able to see that these two situations are the same, and that multiplication of a fraction by a whole number and a whole number by a fraction commute. Barr is thus able to reach the following two conclusions. Number one, a whole number can be repeated a partial time by multiplying it by a fraction. To multiply a whole number by a fraction, divide the whole number by the denominator, then multiply it by the numerator. Number two, multiplication of a fraction and a whole number commute. You can do it in either direction and you'll always get the same answer. Unit 1.22, multiplication of a fraction by a fraction. Motivation. In another business arrangement, Barr contributes 400 gold to a business transaction, just like that of Bayes, and Rom contributes 200. After the entire expedition is over, and after Bayes has collected his fee, we find that the income is 1,572 and 3/4 of a gold coin. Using the method that he just figured out, Barr is able to split up the 1,572 among the two investors. And once he has done that, Barr gets 1,048, and Rom gets 524. Now the problem is that he's not sure how to split up this 3/4 of a coin. He knows from the prior method that he's entitled to 2/3 of it and Rom is entitled to 1/3. But how is he supposed to figure out what 2/3 of 3/4 is and what 1/3 of 3/4 is? He realizes that this is also a partial repetition, which leads him to the following question. How does one find the result of repeating a fraction a partial number of times? First, he's going to consider Rom's share. He's going to think about 1/3 times 3/4. To do this, he's going to use the same kind of reasoning that he did when he repeated a whole number a partial number of times. He's first going to take the units of the number being repeated a partial time, 3/4, so let's draw that. He's going to take each of these units and he's going to split them into 3 pieces, since there's going to be 3 equal shares of all 3 of those units, and Rom will be entitled to 1 of them once it's broken up. So let's look at what happens when it's broken into 3 shares. 2 slices for 3 shares. Each of these gets cut into 3 equal shares. Okay, that's what it looks like. And Rom will only get 1 share out of each of those 3. So 1, 2, 3. That's Rom's share after each of these is broken up. Now, first of all, how large are these pieces? The pieces were originally such that 4 of them were required to make a whole. Then each of those pieces was broken into 3 pieces. That means 3 times more of them will be required to make a whole. Therefore, each of these shares is 1/4 times 3 on the bottom, which is 1/12. So the new denominator is 12. There were 3/4, and each one of those 3 pieces got broken into 12ths. And from each of those pieces, Rom was only given 1. So as a result, at the end of the day, Rom is going to get 3/12. 3/12, of course, simplifies to 1/4 using a prior induction. And so now we know how much Rom is going to get. Now, Rom knows from subtraction that he's going to get 1/2 of that partial coin, but he wants to continue working this out in case he has to multiply fractions in the future. He wants to find a general method for multiplying fractions. And so he's going to figure out 2/3 times 3/4. Now, just like last time, he's going to divide each of these fourths into 3 parts, since he gets 2 out of 3 shares. Now, he gets 2 of each of these 3 shares, so the part that's his looks like this. Notice how in each of the parts that got split up, he got 2 of the 3 subparts. He knows that the total number of parts he got was 2 times 3. Since there were 3 parts, for each of those parts, he got 2 subparts, which is 6. How large are each of these parts? Well, each of the fourths got divided into 3 separate parts, which means 3 times more of them are required to make a whole. That's 3 times 4, which is 12. As a result, Rom knows that he's entitled to 6 parts out of 12 of this coin, which reduces to 1/2 using one of our prior inductions. Now, in both of these calculations, Barr saw that he multiplied the numerators together to find the new numerator of his fraction, and he noticed that he multiplied the denominators together to find the new denominator of his fraction, and so he wants to know if that is the method that will work every time. So now he has to use these and then generalize based on the nature of the method to see that it works every time. So now I'm going to work through the same example example again, but I want you to this time think about the general arguments. Try to see how the reasoning I engage in here applies to any situation, not just the particular situation I'm going through right now. For each of the pieces, which is represented by the second numerator, those pieces are cut into some number of pieces equal to the first denominator. So that means they're cut up, in this case, into 3 pieces. For each of those pieces, a number of sub-pieces are allocated equal to the numerator of the first fraction. For all of these 3 pieces that were originally here, 1, 2, 3 in this case, 2 of those were actually repeated. So as a result, the number of pieces that actually get allocated is always the first numerator times the second numerator. Now, to find the denominator, we consider the fact that we already had partial pieces. Pieces that are so small that 4 of them were required to make a whole, or a number of them equal to the second denominator was required for pieces of that size to make a whole. Since each of those parts are being split into a number of subparts equal to the second denominator, the number of the new subparts required to make a whole will be the product of the 2 denominators, in this case, 3 times 4. Thus, the denominator of the product will always be found by multiplying the 2 denominators. And of course, once again, we get 6 over 12. So that's the general argument. Conclusion. To add a fractional quantity to itself a partial quantity of times, or to multiply a fraction by another fraction, simply multiply the numerators of the fractions. This gives the numerator of the product. Multiply the denominators of the fraction, and that gives the denominator of the product. So once again, we have shown the observations and reasoning steps which are required to prove an idea that is often taken for granted. The idea of repeating a quantity a partial quantity of times. Reproving simple ideas like this will be good practice for when we prove more advanced physics subjects, such as electromagnetism and thermodynamics. Once these concepts are fully connected to the evidence that proves them, we will be able to use them in a more powerful way to reformulate flawed theories of quantum mechanics and general relativity. So I'll see you next time as this inductive journey continues. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.